Have you ever wondered where most of our harmful waste go? Apart from its extensive risk to the environment and humankind, environmental scientists and engineers have come up with multiple methods to dispose them in innovative ways. Good day everyone, we are Group 8 and we will be presenting the treatments for hazardous wastes. But before enumerating the treatment methods, what does it mean to treat hazardous waste? It is a procedure of waste undergoing physical, chemical, and biological processes to reduce its quantity and ensure the security and safety of the community and environment. First up are the explained methods of biological treatments for hazardous waste. Biological treatment of hazardous waste uses microorganisms to break down toxic compounds into harmless byproducts. This low-cost, eco-friendly method includes techniques like an in-situ remediation, composting, and treating both liquid and solid wastes. The most common system or methods are enumerated below, which is the anaerobic digestion, aerated lagoons, activated sludge systems, trickling filters, and waste stabilization ponds. First is anaerobic digestion. It is a biological process where bacteria break down organic waste like manure, food scraps, and wastewater sludge in the absence of oxygen. This process produces biogas, a renewable energy source made mostly of methane and carbon dioxide. Biogas is generated in sealed reactors and can be purified into biomethane for use as a green fuel. Alongside biogas, the process also produces digestate, a nutrient-rich byproduct. While it can improve soil health and reduce the need for chemical fertilizers, digestate must be managed carefully to avoid nutrient pollution. With proper treatment, anaerobic digestion supports waste reduction, energy recovery, and sustainable agriculture, making it a key part of circular bioeconomy. We then move on into the activated sludge system, which is widely used for biological processes for treating hazardous landfill leachates. It relies on microorganisms that consume or break down complex organic carbon and nitrogen compounds present in the waste. This process includes aerating the wastewater either by pumping air or oxygen into the tank or using surface aerators to maintain aerobic conditions, which help the microbes thrive. To improve efficiency, microfiltration membranes with a backflushing technique are used. Backflushing periodically cleans the membranes, prevent clogging, and maintaining steady filtration. This setup allows for better control or sludge retention time and supports the microbial community needed to degrade the stubborn organic pollutants. Next, a trickling filter is a biological treatment system where hazardous waste flows over a fixed bed of inert materials. Microbial biofilms growing on the surface break down the pollutants as the waste trickles through. Aerobic conditions are maintained by either fans or natural airflow to support microbial activity. Tests on wastewater from dye and varnish industries showed up to 85% removal of chemical oxygen demand, making trickling filters highly effective for treating strong, hazardous wastes. This method combines biological degradation and air stripping, proving to be a strong pre-treatment option for industrial wastewater. Then, waste stabilization ponds are engineered water bodies that treat hazardous sludge through natural processes involving sunlight, wind, and microorganisms. These ponds are low cost, easy to construct, and effective for treating wastewater, often used alone or combined with other systems. They can also support uses like agriculture and landscaping. These are the three main types of ponds. Facultative ponds have three layers: an oxygen-rich surface with algae, a mixed middle layer, and an oxygen-free bottom where natural processes break down waste efficiently. Anaerobic ponds treat wastewater without oxygen, reducing organic load and producing granular sludge that is easier to manage. However, these ponds can generate odors and require several months to establish stable digestion, especially in cooler climates. Aerobic ponds uses oxygen, sometimes with mechanical aerators, to maximize the breakdown of organic matter. and reduce harmful bacteria. Maturation ponds are a type of aerobic pond designed to polish the water, ensuring safe, high quality effluent. And for the last method, aerated lagoons are deep treatment ponds where mechanical aerators pump air into the wastewater to help break down organic matter. Unlike natural ponds that rely on algae for oxygen, these lagoons actively add oxygen to speed up the process. They fit between simple oxidation ponds and more complex activated sludge systems in terms of treatment strength. The types of microbes inside vary depending on nutrients and treatment progress. A simple design using two lagoons with facultative aerobic conditions is an effective and affordable way to treat landfill leachate. Performance depends on controlling factors like pH, oxygen levels, how often and how much air is added, and the time wastewater stays in the lagoon. Suggested improvements include using intermittent or nighttime aeration to save energy, installing baffles to improve water flow, helping microbes adapt to toxins, and combining lagoons with constructed wetlands. Treated water can also be reused in agriculture through ferti-irrigation, closing the resource loop. Biological treatment of hazardous waste is an environmentally friendly approach that uses natural or engineered biological systems to sustainably manage and recover resources from various types of hazardous waste in both aquatic and soil environments. It offers multiple treatment options such as aerobic and anaerobic processes, composting, and advanced biotechnologies, which can also be integrated with physical and chemical methods to improve effectiveness. However, biological treatment is complex and site specific, requiring a thorough understanding of waste characteristics and environmental conditions for proper optimization. Some emerging technologies like nanotechnology and biosensors are still in development and not widely available. Overall, successful implementation depends on managing multiple factors and ongoing research in microbiology and process engineering.
For this part of the presentation, we will be talking about the chemical side of treating hazardous waste. Let's begin by understanding the fundamental principle of chemical treatment. Chemical treatment uses carefully controlled chemical reactions to transform hazardous substances into safer form. Think of it as a molecular level recycling. We are not just removing the problem elsewhere, we're actually changing the chemical structure of the most dangerous materials. These reactions can neutralize extreme acidity that would otherwise burn through containers and contaminate groundwater. They can reduce toxicity levels that pose lethal risk to human and wildlife. They can also stabilize highly reactive compounds that might otherwise explode or release toxic gases. This process serves as a protective barrier in hazardous waste management. It prevents toxic substances from contaminating our air, soil, and water systems before they can cause irreversible damage. What makes this approach so powerful is its preventive nature. Rather than dealing with contamination after it occurs, which is often impossible or extremely expensive, chemical treatment addresses the hazards at its source. In essence, we're turning dangerous waste into manageable material before it can harm anyone or do anything bad. And here we have the three main methods. And the first one is ion exchange. This replaces dangerous ions in a solution with safer ones using synthetic resins. This is widely used to purify water in industries like electronic and power generation. It also helps recover valuable metals from the waste streams. And for the next one is precipitation. Chemical precipitation involves adding chemicals to a liquid waste to form solid particles or precipitates. These then are filtered out and is especially effective for removing heavy metals, suspended solids, and phosphate from distilled wastewater. And for the last one is oxidation reduction or redox. chemically transforms hazardous substances by transferring electrons. For example, it can convert highly toxic chromium-4 into its safer form, chromium-3, or oxidize cyanide into harmless compounds. And these methods can also be combined, for example, redox solver precipitation to improve treatment efficiency. Chemical treatment offers three core benefits. First, it reduces how dangerous a waste is by neutralizing toxicity or corrosiveness. Chemical treatment helps protect workers, communities, and natural ecosystems. Second, it enables resource recovery. Some chemical methods allow us to recover valuable substances like oils, glycols, and metals from what would otherwise be thrown away. And for the third one is chemical treatment aligns with the circular economy. Rather than seeing waste as a final product, we view it as a potential input, something that can be repurposed, reused, or safely returned to the environment. This does not only save money, but also improves corporate reputation and demonstrate environmental responsibility. While chemical treatment is powerful, we must acknowledge its limitations to use it. Most effectively, waste specificity is perhaps the biggest challenge. There is no universal solution. Different contaminants require different methods of treatment. A method that works perfectly for heavy metals might be useless for organic solvents. This means every waste stream requires careful analysis and often custom treatment protocols, which adds time and cost to the process. Secondary waste generation is another significant consideration. Some methods, particularly precipitation, can actually increase the total volume of waste by creating sludge that must be further treated or disposed of safely. You solve one problem but create another one that still needs management. Safety concerns are also inherent when working with powerful chemicals. The treatment process itself involves handling corrosive acids, acidic bases, and reactive compounds. Workers need extensive training, proper protective equipment, and facilities must maintain strict safety protocols. The cure can be as dangerous as the disease if not properly managed. Additionally, incomplete reactions can create intermediate compounds that are still hazardous, sometimes even more dangerous than the original waste. This is why chemical treatment requires not just technical expertise, but also careful long treatment, monitoring, and managing. Despite these challenges, the benefits outweigh the limitations. When chemical treatment is properly implemented with appropriate safeguards and expertise. Let's examine how these principles work in practice, starting with industrial water treatment. Chemical treatment plays a crucial role in protecting our water systems from industrial contamination. Redox reactions are commonly used to address two particularly dangerous pollutants, namely ammonia and hexavalent chromium. Ammonia, while seemingly harmless, can devastate aquatic ecosystems by causing eutrophication, an excessive plant growth that depletes oxygen and kills fish. Redox treatment oxidizes ammonia into nitrate, which are far less harmful to aquatic life. Hexavalent chromium is even more serious. It is a known carcinogen that bioaccumulates in the food chain. Redox reactions reduce it to trivalent chromium, which is not only harmless, but actually beneficial in small quantities. A compelling real-world example comes from the mining operations in the Appalachia region, where acid main drainage was contaminating entire river systems. Using lime and limestones to neutralize the acidic water and precipitate heavy metals, treatment facilities drastically improved water quality and restored aquatic habitats. Rivers that had been lifeless for decades began supporting fish populations again. This demonstrates how chemical treatment can reverse decades of environmental damage and restore natural ecosystems. The pharmaceutical industry showcases the chemical treatment's versatility through its complex waste challenges. Manufacturing generates highly acidic or alkaline waste containing toxic metals and organic compounds. Treatment follows three critical steps. First, pH neutralization using sulfuric acid or sodium hydroxide to correct extreme pH levels from synthesis and cleaning operations. Second, precipitation. It removes heavy metals by converting them into filterable solid particles. And for the third one is ion exchange. It polishes water to remove the remaining ionic contaminant. This systematic approach ensures pharmaceutical companies meet the strict discharge regulations while protecting public health and preventing overcorrection that could create secondary waste problems. Power generation and electronics demand ultra-pure water, making ion exchange systems absolutely essential. These systems remove dissolved salts and trace contaminants that could damage sensitive equipment in power plants. Even microscopic minerals can cause boiler scaling, turbine corrosion, and efficiency losses. Electronic manufacturing requires even stricter purity. Semiconductors facilities produce water so pure that contaminants are measured in parts per billion. This prevents microscopic impurities from destroying million-dollar processor batches. Beyond protection, ion exchanges offer economic benefits by recovering valuable metals from waste streams, making the process both profitable and environmentally beneficial.
Have you seen that animated film where a little robot cleans up massive piles of trash, compressing them into small cubes and stacking them into towering structures? Yes, I'm talking about Wall-E. The endless waste you see in the background is a perfect example of land disposal in action. But today, I'll be talking about land disposal of hazardous waste. Land disposal refers to the placement of hazardous waste into or onto land. Disposal facilities are specially designed to permanently isolate the waste and prevent the release of hazardous pollutants into the environment. This is a common method used when waste cannot be recycled, reused, or safely treated. The main land disposal units include landfills, surface impoundments, waste piles, land treatment units, and injection wells. Let's begin with landfills. Hazardous waste landfills are specialized facilities excavated for disposing of non-liquid hazardous waste. They're built away from environmentally sensitive areas, and they must follow very strict rules. Hazardous waste landfill must have double liners, two leachate collection and leak detection systems, wind and runoff control, and at least 3 meters of separation from bedrock or groundwater. They are inspected several times per year to ensure they follow environmental laws. But in many developing countries, landfills are just open dumping grounds. If waste leaks out, it can cause air pollution, toxic exposure, and even contribute to global warming. An example of hazardous waste found in landfills and PCBs are polychlorinated biphenyls. These are highly toxic and were banned. They are found in old electrical transformers and are dangerous to both humans and animals. While industries that use hazardous waste landfills include chemical manufacturing, pharmaceuticals, battery manufacturing, like for things like stabilized lead contaminated residue. Another example is the one we see in Wall-E. But except that in Wall-E, those are not hazardous waste materials. That is an example of an open dump landfill. Next, we have surface impoundments. These are pond-like structures, either natural depression or man-made basins. They are designed to hold liquid hazardous waste. They are lined with protective materials to prevent leakage and take note that it's only for temporary storage and treatment. They are used to store and sometimes treat industrial wastewater, landfill leachate, mining runoff, and even agricultural drainage. Now, let's talk about waste piles. Waste piles are non-containerized mounds of solid, non-liquid hazardous waste that are temporarily stored or treated. Unlike surface impoundments, they are for solid only and are mainly used for storage before the waste is moved or treated. Industries that use waste piles include construction and demolition for contaminated soil or rubble, metal fabrication for slag and fly ash, and mining and mineral processing. Next up is land treatment units, or LTUs. They are more environmentally integrated. They treat hazardous waste by applying it to soil surfaces where natural microbes and sunlight help break it down. These processes work best in the unsaturated zone. That's the land above the groundwater table. What makes LTUs different is that they don't need liners or leachate systems because the soil itself becomes the treatment medium. According to the EPA, land treatment involves supplying or mixing hazardous waste into the upper soil layers to degrade or immobilize toxic chemicals. Industries using land treatment units include oil refining for oily sludge, food processing, biotech, and agrochemical companies like pesticide waste. Finally, we have injection wells. These are deep wells usually drilled thousands of feet below drinking water sources. They're used to inject hazardous and non-hazardous liquid waste into deep rock formations. There are two main types: Class 1 wells, which are still used for deep injection at industrial sites, and Class 4 wells, which are now banned because they were too shallow and pose a risk to drinking water. Industries that use injection wells include petroleum refining, chemical productions, and pharmaceuticals. Now that we've talked about the different methods of land disposal, let's now talk about their closing method because everyone needs their closure. Starting with landfills. If a landfill shuts down, it undergoes closure with waste in place. These include stabilizing the remaining waste, installing a final cover or cap, long-term leachate and groundwater monitoring, and post-closure care for 30 years or more. For surface impoundments, there are two closure options. First is clean closure, where all liquid and sludge is removed and the site is decontaminated. Second is closure with waste in place, which requires stabilizing sludge, installing a cover or cap, and long-term monitoring of nearby groundwater. For waste piles, if all waste is removed, it can undergo clean closure since waste piles are only temporary. For land treatment units, units must stop waste application. The soil is sampled to ensure contamination is within safe limits, and if needed, soil excavation and treatment may be done. Post-closure monitoring is also often required to check for leaching or toxins. Lastly, for injection wells, they are sealed and plugged. The injection zones are monitored for pressure and migration. Long-term groundwater testing may also be required. That's all for closing. Now that we've looked at the different types of land disposals and their closing methods, let's talk about their advantages and limitations. Firstly, the advantages. Number one, it's cost effective. Land disposal is generally cheaper than other options like incineration or advanced chemical treatment. It's a practical solution, especially for large volumes of waste. Number two is it's established and regulated. It's widely used and governed by strict environmental laws such as the Resource Conservation and the Recovery Act in the US. Number three is it's good for treated waste. If the waste is already stabilized or detoxified, land disposal offers a relatively secure long-term storage method. Number four is simple and available. Many countries already have the infrastructure to support land disposal, making it an accessible option. But There are also important limitations. First is the risk of contamination. If liners break down or structures fail, hazardous chemicals can leak into the soil or groundwater. Second is the long-term responsibility. These sites need to be monitored and maintained for decades, even when they stop accepting waste. Third is not always qualifies. Some types of hazardous waste must be pre-treated before they can legally be land disposed. Fourth is the public concern. People often don't want facilities near where they live. This is known as the NIMBY effect, or the not in my backyard. Lastly is the limited suitable locations. Finding geologically safe and publicly acceptable sites for disposal is a major challenge. And that's all for advantages and limitations. Land disposal is often the final option for hazardous waste. It's used only when biological or chemical treatments aren't enough. While effective, it comes with long-term risk that requires strict monitoring and care. Together, we've explored the three major treatment methods: biological, chemical, and land disposal. Each plays a key role in reducing the dangers of hazardous waste. Thank you for listening, and we hope you now have a better understanding of how these technologies help protect our health and environment. On the following pages are our references.